This webcast on the HSA Foundation's 1.1 Spec launch. I'm John Glossner, president of the HSA Foundation, and I'll be walking you through what's new in the 1.1 specs. So first, a little bit of an overview. So the HSA Foundation was founded in June 2012 with the mission of developing a new platform for heterogeneous systems wherein the underlying processor details are abstracted from the programmer such that they don't have to worry about a specific instruction set. So I'm happy to say that the 1.1 specifications are backward compatible with the 1.0 ones, which were originally released in March of 2015. And we also have compatible hardware now available just recently from AMD with their Carrizo, and I will be giving some performance improvement measurements based on an earlier AMD part. So the members driving the HSA are across a broad range of industry segments, from software to tools to semiconductor manufacturers. The founders being AMD, ARM, Imagination, MediaTek, Qualcomm, and Samsung, and promoters being LG Electronics and GPT. So just as a background, what is the problem that's being solved by HSA? So first, heterogeneous processors are widely available. Pretty much every SoC shipping is a heterogeneous processor. They have huge compute capability and many acceleration units on them, from GPUs to DSPs and FPGAs. And at the high end, most already have coherency, and that is migrating into the mainstream mobile and consumer areas. However, there's no standardized programming model. Trying to scale any of these systems to larger and larger devices is very difficult, and right now there is no portable ecosystem for taking code and being able to run it on different systems. What the HSA Foundation is doing is bringing that abstraction for compute applications so that you do not need to worry about the underlying processor that's executing, and it's scalable and highly optimized. So first, it is an open architecture and membership is open to all. Effectively, there are a set of specifications, the programmer's reference manual, the system architecture, and the runtime. These are all delivered royalty-free, unencumbered in IP, and effectively they talk about how to abstract the processor and put them into a system in a way that's instruction set agnostic and works for CPUs, GPUs, DSPs, and we continue to add more and more types of instruction sets. We do that effectively with a virtual instruction set architecture that then gets finalized into each of the specific instruction sets, and we'll talk a little bit more about how that happens. One of the key benefits of HSA is a single source programming model, and specifically without requiring you to learn a new language as a developer. We support multiple languages, including OpenCL, C++, Python, as well as others. And so you can continue as a developer to develop using whatever language you're comfortable with. And we've put both the control, the host, and the agent or kernel code written in the same programming language in the same single source file. We get these benefits by having a single unified coherent address space, which allows free sharing of pointers. So if you're the DSP in this system, you don't have to copy the data back and forth between the CPU and whatever agent is in the system. And so we try to maintain a similar kind of model as what you would think about with a multi-core CPU. In terms of identifying the parallelism within the instruction sets, the syntax is the same as anything you're used to programming in before. So OpenCL inherent in the language, OpenMP with the set of constructs that they use, C++, AMP, and others. So whatever syntax for multi-core, we want to abstract and now have that be active over multiple heterogeneous cores. And the way that's done is with HSAL, the HSA intermediate language. It's a virtual instruction set, something on the order of like Java is for CPUs and the Java programming language, but effectively it's a low-level, RISC-based virtual machine that gets dynamically translated at runtime into whatever heterogeneous processor you're executing on, with the key feature being that all of the parallelism in that virtual instruction set is captured from the high-level language, and it's able then to be optimized for different types of processors. So we provide a core runtime API to interface all of that, and a key point is that it's at user mode. So no hopping back and forth between a CPU's operating system to be able to do simple things like dispatch programs to various processors. And that includes pretty much all the stuff you would think you would need: how to initialize and shut down a system, how to send notifications back and forth both synchronously and asynchronously, how to signal various things, how to architect the queues to put things into the queue, and how to do memory management. One of the unique benefits of what we have done at the HSA Foundation is to open source all of our tools, including OpenCL compilers, and there are other open source tools for Python and for C++. And so you can pretty much use your favorite tool chain to be able to generate HSA code. So once you generate HSAL, there's another open source project that will take that HSAL and read it into GCC's front end, which allows for finalization of virtually any instruction set, since so many are supported. You can do the same with LLVM as well, off of the original OpenCL tools or any of the other tools that are widely available. And there's also open source reference implementations of the runtime that you can go and get from HSA's GitHub site. Download, compile, and run it and try it yourself. A key point is that our memory model is compatible with all of the high-level languages that we've been talking about. So that defines a relaxed consistency, which is good for parallel execution, and it defines also the visibility and the ordering of loads and stores between all of the different various threads. And that's done in very much the C++ style with load, acquire, store, release, and fences. So the baseline, the 1.0 specifications released in March of 2015. So this provided the underlying set of APIs to be able to build a whole entire system with this level of abstraction on a heterogeneous system, making it look like a CPU. However, there were a lot of features that weren't specified and did not need to be specified when it was only a single vendor that was implementing the entire system. It was also primarily targeted at CPU and GPU, although there is some support for other types of processors in the 1.0 specifications. A key point being the cache-coherent shared virtual memory, and it also included the user-level queues and user-level dispatch and signals. So that was the baseline. And so now, with the new spec launch of the 1.1, we're excited to have added some new features and to have enhanced some of the existing features. So the first thing, which we promised, is that it would be backward compatible. So there are no hardware changes required for the version 1.1 spec. We're only talking about software. A key, very important addition now is the multi-vendor specification. Things that did not need to be specified when it's all one vendor's IP being integrated now need to be specified when you want to take a CPU from, let's say, ARM, and maybe a GPU from Imagination and a DSP from GPT, and put them all together in the same system. Now you need to see and be able to see transparently places like where page tables are stored and things like this. So these are all now specified in the multi-vendor, and a vendor-neutral device driver is also provided to go along with that to make the integration much quicker. The version 1.1 also has a wider range of instruction set and processor types supported. DSPs in particular and image signal processors now have support in the virtual instruction set. Signals got an upgrade by allowing multiple waits, so you can be waiting on multiple signals as an agent. There are certain forward progress rules that we're able to make. Part of that is because we have a formal definition of the memory model that's been proven in some various modeling for memory, cat and herd in particular. We also added the concept of a non-temporal memory access so that you could tell the finalizer when a value might not be reused again, which allows certain optimizations in the memory system. And multiple agents can now share images as well. The finalizer was improved in this release to provide a kind of standard code object which matches many of the tools that are already in existence today, and for version extensions. So you can request now a very specific version of a set of HSAL code that was generated. A huge addition is a profiling API. So, normally when you're profiling a processor, you're thinking about the low-level instruction set. Here, we're talking about profiling across different processors at different times, all with the same API. So you get access to hardware counters and timestamps that work across multiple different instruction sets, and we provide a way that you can ask for the data back and do performance analysis, and then possibly use that information for things like profile-guided optimizations. We also have high-level debug information in HSAL that can be included in the generated code object. Not quite at the same point as the profiling API, but the first steps to be able to also begin to debug heterogeneous systems from the same common view without needing multiple tool sets from multiple different tool chains to be able to see all of the different features. Okay, so let's talk about some performance. So the best thing for HSA is for most developers to never even know HSA is sitting there. It's weaved into the fabric of all of these heterogeneous systems, but hopefully at the developer level, the language features at that developer level will be automatically translated and take advantage of the parallelism. So Continuum Analytics is one such company that has an open source Python compiler, Numba, that has direct HSA support and automatic parallelization of any universal function. And I don't mean some library hidden underneath that is optimized that just gets called. Universal functions are a type of Python function, like doing a map, the same operation over an array, these types of things. So this Numba compiler will automatically parallelize these universal functions, which is just pure Python code. You only have to tell it that you want an HSA system and target an HSA system, and then the rest of it will be automatically split up, parallelized from the same source, and Continuum has shown speed ups anywhere from 2 to 200x depending on the application for doing that. Again, with no developer support required from the development programmer. Northeastern also recently did a bunch of benchmarks looking at the performance of HSA. This was done on a Kaveri system. I'm showing just a couple of them, an FIR, which is memory intensive, and AES encryption, which is compute intensive. And so you can see here the normalized execution time, so lower is better. And you can see in some of these cases, HSA is 10x improvement. So think about this. So our goal was to not pay a penalty for abstracting out the underlying instruction set. And I'm not saying in all cases, not all algorithms run faster, and so you can read the full paper and see the reasons why some of these do run faster. But a lot of it has to do with user-level dispatch and user-level queues. And that provides a huge performance, and that's architected into the system. And it has to be architected, or you cannot take advantage of these kind of things in a general system. So, this is comparing against OpenCL 1.2 as the baseline, and showing OpenCL 2.0 and then HSA. And so, again, meeting the intended goal of no performance degradation for a much, much higher level of abstraction. So we can also have recently seen a paper published by National Tsinghua University and National Taiwan University where the GPU itself is virtualized. So typically you think about virtualizing a CPU and running multiple copies of an operating system there. They did the same thing for a GPU and found, except in a couple of cases, they achieved 95% of the native performance in most applications executing on the GPU. So if we take a look, so where has HSA come? So we have a single source programming using whatever the developer's currently favorite tool chain is and supporting all of the standard programming languages, not forcing the programmer to switch and learn a new language, but taking advantage of some of the features in the language that are already there. We get a lot of that performance by eliminating data copies with the cache-coherent shared virtual memory. That allows you to pass pointers around between the various different agents, and they will execute without having to do a copy. There is a user-level dispatch language, and it's architected so all agents know how to talk to those queues and execute out of those queues. And removing all of those software layers where typically you would have had to talk to the operating system, bringing that up to a higher level has made the whole entire system more efficient. The instruction set is agnostic. We have implementations running on CPUs, GPUs, DSPs, and more from a wide range of vendors. And particularly, everything is open source. You can go get the runtime. All the APIs are public, and now the 1.1 APIs as of May 31st, 2016 are also now public. It's open access to HSA. You can come join us and help us with the next set of developments. So really, if we step back and look, the first couple of years were about getting the hardware correct. And cache-coherent shared virtual memory is now the de facto methodology for these heterogeneous systems, and HSA sits on top of that. And so the next couple of years were about how to take advantage of that hardware that sat there using any programming language. And so that was last year's specifications. And so it's taken some time to implement that, but I'm happy to say we now have some hardware platforms arriving that can execute the full 1.1 specifications. We have excellent preliminary performance results, and we have been able to achieve our goal of no performance penalty for this higher level of abstraction. And now that the multi-vendor specifications are released, we'll be excited to see integration of IP blocks from all different vendors as they support their customers. So that's it. Thank you. This is the Spec 1.1 launch update.